Dear students, welcome to presentation on equation of continuity and Bernoulli's principle. These are topics in module 6 of Sensors and Transducers. This is being presented by Vimalkumar V, Assistant Professor, Department of Applied Electronics and Instrumentation, Rajagiri School of Engineering and Technology. The continuity equation in fluid dynamics describes that in any steady-state process, the rate at which mass leaves the system is equal to the rate at which mass enters the system, assuming there is no storage. Consider this system. You can see fluid flows in with a velocity v1 and fluid flows out with a velocity v2. In case of compressible liquids, the density at A1 will be different from density at A2. So we have to take in that ρ1 v1 into A1 will give you the mass which is entering, and similarly ρ2 v2 into A2 will give you the mass which is leaving. If there is no storage, both should be equal. So ρ1 A1 v1 equal to ρ2 A2 v2, where ρ1 ρ2 are densities at A1 and A2. Compressible, we can say ρ1 and ρ2 can be equated to a constant rho. That is, density will be constant throughout the flow. So we can simplify this as rho A1 V1 is equal to rho A2 V2. Rho will cancel out and we will get A1 V1 is equal to A2 V2. This is an equation of continuity or continuity equation. This has wide application for flow meters, and similarly Bernoulli equation has great significance in differential pressure kind of flow meters or head type flow meters. Let us see Bernoulli's principle. Bernoulli's principle states that an increase in the speed of a fluid occurs simultaneously with a decrease in static pressure or a decrease in fluid's potential energy. At any point in the path of an incompressible fluid through a pipe, the sum of pressure plus rho v square by 2 plus rho gh is a constant. Here rho stands for density of fluid, v is the velocity of flowing fluid, and g is acceleration due to gravity, and h is the height of the fluid. This will be clear when we consider this. We have 2 points 1 and 2. At point 1 we have a pressure P1 where fluid is flowing with a velocity v1 and the height there is h1, and in point 2 we have pressure P2, the height there is h2 and velocity is v2. So we have considered points 1 and 2. So the previous relation holds here. So P1 plus rho v1 square by 2 plus rho g h1 is equal to P2 plus rho v2 square by 2 plus rho g h2. This is Bernoulli's principle or Bernoulli's equation, and we will see how this is derived in the following slides. This is based on the principle of conservation of energy. The fluid considered is assumed to be incompressible, non-viscous, flowing with same temperature throughout the pipe. That is, if we consider 2 points, temperature is same. It is flowing without storage or leakage. We also assume that density is constant throughout. Then we consider a pipe of variable area with fluid entering section 1 with area A1 with pressure P1 and leaving section 2 with area A2 against a pressure P2. This is the figure. You can see section 1 on the left, that is at a height h1 from the reference. There the area is A1, the pressure is P1 and fluid enters with a velocity v1. Similarly on the right side at a height h2, the area is A2 and the fluid flows with a velocity v2 against a pressure P2. Now we are assuming the case when the fluid is flowing for a time delta t. We are assuming a small time delta t and considering what all happens within that time to calculate what is the work done by pressure during that particular time delta t, t1. So P1A1 is the force that is acting on the left side, and because of this, if it acts for delta t, fluid flows with a velocity v1, and similarly on the right side, that is you can similarly on the right side we see that fluid flows with velocity v2 against force due to p2. Now you can see on the left side as well as on the right side a circular section is indicated by darker blue shade. So we assume that that section is moving to the next marked section during time delta t. So see, it has moved during time delta t. You can see that the section on left has moved. Similarly, the section on right has also moved. So in delta t time, that movement is there. Now the volume on left and right are both equal, and see, but the distances will be different. Delta x1 will be different from delta x2. Now let us see, the work done on lower end of the fluid is given by P1A1 into delta x1. Now A1 into delta x1 is the volume of fluid that passes through region 1 as well as region 2 in time delta t. The work done at the upper end or the right half is W2. Now the fluid is leaving against pressure P2. So actually the movement is taking place against the force. That is why the work is negative. So minus P2A2 delta x2, that is minus P2 delta V. Thus the net work done by these forces in time delta t is W equal to P1 minus P2 into delta V. That is nothing but W1 minus W2. So we get P1 minus P2 times delta V, where delta V is the volume. The work W show itself as change in kinetic energy and potential energy. So W is equal to delta K, that is change in kinetic energy, plus delta P, that is change in potential energy. Now change in kinetic energy will be the difference of the kinetic energy of the fluid mass which is leaving and the kinetic energy of the fluid mass which is entering. We are assuming that for a time delta t, the mass passing through the system is delta m. Delta m is the mass passing through pipe in time delta t. We are assuming delta m to be that mass. Now calculating delta ke. Delta ke equal to delta m into v2 square by 2 minus delta m v1 square by 2, that is we are using the formula half mv square for calculation of kinetic energy. Now to calculate change in potential energy, the potential energy change takes place due to change in height of fluid, height of the points where fluid enters and height of the point where fluid leaves. We have assumed that h2 is the height at which the fluid leaves. So the potential energy at that point will be delta mgh2, and if we subtract the potential energy when the fluid enters, we will get the change in potential energy. So delta PE equal to delta mgh2. So that is delta mgh2 is the potential energy when the fluid leaves minus delta mgh1, the potential energy when the fluid enters. We take the difference, we obtain delta mgh2 minus h1. So we obtain the change in potential energy. Now we have change in potential energy and change in kinetic energy. Now we can equate it to the expression of W. Now W was P1 minus P2 into delta V, where delta V was the volume. So when we equate that, we obtain P1 minus P2 into delta V equal to delta M into V2 square minus V1 square divided by 2 plus delta Mg H2 minus H1. If we rearrange this, we obtain, before that, if we divide both the sides by delta V, on the left side delta V will cancel out. On the right side, wherever there is delta M by delta V, that is mass divided by volume, that gives you density rho. So we substitute delta M by delta V by rho everywhere on the right side, and we obtain this expression. Now we can rearrange this to obtain the expression as P1 plus rho V1 square by 2 plus rho G H1 equal to P2 plus rho V2 square by 2 plus rho G H2. Now we can conclude that we have obtained the expressions at 2 points. We note that sum of pressure plus rho times V1 square by 2. Now this term is denoting kinetic energy. The first term P was denoting energy due to pressure. Now rho G H1 is the term which denotes potential energy. So the essence is that at in 2 points, sum of pressure energy, kinetic energy and potential energy will remain same. Thus we have P plus rho V square by 2 plus rho GH is a constant. This is Bernoulli's principle. This has application in head type flow meters. These are the references. Thank you.